All right, measures of variation, with the main focus today being on something called standard deviation. So the first thing we're talking about is range, because we're focused on how spread out things. So range is one indicator. Range is our highest number minus our lowest number. And range isn't always the best thing to look at. Range is greatly impacted by outliers. Any outlier can make your range larger, and that one number might not be relevant compared to the rest. It might just be so far out, giving you a large range, but really, most of the other data is quite compact. So that's where we start looking at standard deviation. And standard deviation is a measure of how spread out the data is. All right, how spread out, what's the dispersion of this data? In plain English, it's a way of describing how spread out a set of values is around its mean. How far away do we go from that mean, that X bar situation? So if we look at these examples below, if everything, like the first example, has its standard deviation, if everything has the same number as the mean, there is no spread. Everything is right there. And as we go across, we see it gets more and more spread. For the second one, we have a standard deviation of 0.8. Right? There's a lot of things happening at the mean. The frequency is 3. And then we start getting out to 3 and 5 with frequencies of 2. As we move from here to here, our mean gets smaller and more numbers are away from the mean. We're in that middle one there with 4. 4 had the largest one and it was the mean. Going over here, we're moving away from 4, filling 3 and 5 with more frequency tallies. Finally moving out here, where 4 is still the mean, but we've moved to more frequency tallies in 1 and 7, spreading the data out further. The data is getting wider and wider. So if there is no spread, like the first example, where the mean is the same thing as every number, our standard deviation is 0. But the further we get from the mean, the further spread out we get, our standard deviation grows. So when using standard deviation, keep in mind the following. Standard deviation is only used to measure the spread or dispersion around the mean. Standard deviation is never negative. Standard deviation is sensitive to outliers. A single number can throw off the entire thing and change the standard deviation, as well as the range, as well as the mean and median and whatnot. For data with approximately the same mean, the greater the spread, the greater the standard deviation. And if all values of the data set are the same, the standard deviation is 0. Now we could take some time and go through the whole process of figuring out the standard deviation for this data, but we don't have to do that. What we can do here is just use our calculator. So in this situation, this is our L1. We plug all this data in. And when we plug this data in, under the one variable stat, we're looking for standard deviation. All right, so we got S of X, which is your sample standard deviation, and you got that sigma X, which is your population standard deviation. So if we go through the whole process here of calculating our S of X, our sample standard deviation, we type into L1, we do one variable stats, and our sample standard deviation is 0.477. All right, and we'll talk about what that standard deviation means in a minute. Now going back to an example we had recently. In class recently, we had these 3 data sets. What we learned is that all 3 of them have the same mean of 50. Now if I were to map these out, right, here's data set A. 10, 20, 30, 40, 50, 60, 70, 80, 90. Data set B. We got 3 20s, 140, 150, 2 70s, and 2 80s. All right, and lastly, we got data set C, where we have a 30, 2 40s, 3 50s, 2 40s, 2 60s, and a 70. So in this situation, which data set do you think has the largest standard deviation? It's going to be A. A is the most spread out. The mean is 50, and we're going further away from 50 in A than we are in B and C. The smallest standard deviation would be C. It's the most compact. All the numbers, all the data points are closest to mean than A and B. So if we actually took some time to calculate our standard deviation, our S of x here is 27.38. Our S of x here is 25.98. And our S of x here is 12.25. Clearly showing that A has the largest standard deviation because it has the largest spread, it has the largest variation, it has the biggest distribution of all the data sets. Now, if you look in the classroom on the wall, we have this normal curve graph. It's right above where I sit. With our normal curve, this is going to be something to go back to over and over again. It talks about our standard deviations away from the mean. So if you are one standard deviation away from the mean, you will cover 68% of the data. So from here to here, one standard deviation away, there's 68% of our data. If you go 2 standard deviations away, you'll have 95% of data come in. So if I'm looking 2 standard deviations away, I'm looking from red line to red line. If I go 3 standard deviations away, I almost have all the data, but we got to take into consideration that maybe there's an outlier that's taking it a little bit further so we don't get all 100 covered. So I'm looking from there to there. So there's my 99.7%. All right, so standard deviation, 1 standard deviation away, 68% of the data should lie there. 2 standard deviations away, 95% of the data should lie there. 3 standard deviations away, 99.7% of the data should lie there. So if we look at the next page, I'm just going to erase this here. I'm going to draw this on this page, kind of help me out. So we have a scenario. The IQ scores of American adults are normally distributed with a mean of 100. So our mean in this situation is 100. And what we're told is the standard deviation is 15. So if I go 1 standard deviation to the right, I got 115. If I go to the left, I have 85. If I go a 2nd standard deviation away, I'm at 130. And this way, I'm at 70. If I go a 3rd standard deviation away, I'm at 145. And if I go a 3rd one this way, I'm at 55. So again, the idea holds true. If we're talking about 1 standard deviation away, between 85 and 115 should lie 68% of our data. If we're talking about between 70 and 130, that should be 95% of our data. So the first problem we're looking at says, what percentage of American adults have an IQ of 100 or better? So 100 or better, we're here on this median line, this middle line, and we're going to the right. So in that situation, 100 or better is 50%. It's half the graph. All right, part B. What percentage of American adults have an IQ of 85 or worse? So we're talking 85 or worse. So we are here going that way. All right, so what I think is this. This is how I'd answer this problem. All of this and everything going that way is 50%. The only thing not taken into consideration on that left side is the 34. So the 50% and the 34 shows me that 84% of the graph is not being used. So that left tail would then have to be 16%. All right, so the 50% to the right's not being used. The 34% to the left of the mean's not being used. So that leaves us with 16% being everything to the left of 85. All right. So if we go next, let's see. Next we got 70 or higher. 70 or higher. We're here and we're going everything that way. So we got the 50%. All of this and this way is 50%. We got the 0.34 and the 0.135 to go with the 50. So adding 50%, 34%, 13.5%, C is 97.5%. So 97.5% in this situation of people have an IQ of 50 or higher in this scenario. Between 85 and 115. Well, 85 and 115, that's our nice setup of 1 standard deviation away. So 1 standard deviation away, based off what we've been told, is 68%. All right, part E. All right, A, B, C, D, part 5. So we're talking now 70 to 115. All right, so 70 to 115. All right, so obviously I got my 68% there. I got to add in the 13.5. So 68 and the 13.5, I got 81.5%. If I jump back to numbers, part 6 I'm on now. Part 6, between 55 and 130. All right, so I'm looking now, all right, I got my 95% there from here to here, and I got my little tail. So 95% plus in that situation, that extra 0.24, 97.35%. All right, that's the exact number. All right, but I kind of shortened it with the little tail. All right, part 7, between 145 and 145. Between 100 and 145. So, initial thought, people say this is 50%. No, it can't be 50% because we're missing this extra piece out here. 3 standard deviations away is not the full 50%. But 3 standard deviations to the right, 99.7 divided by 2, we got half of the 99.7, we got 49.85%. All right, so 3 standard deviations to the right, we got 99.7 divided by 2. All right, sorry if that got a little crazy, but I was just trying to get all the ideas out there. All right, so this is what we had here, right? So again, we're starting with 100. 1 standard deviation away puts us at 115 and 85. Second standard deviation away puts us at 130 and 70. Third standard deviation away puts us at 145 and 55. And I used the percentages on the previous chart to help me through. With the last problems here, the first question is saying, what battery would you use? Well, Duracell has a mean of 50 and a standard deviation of 20 hours, meaning that 68% of the batteries are going to have a battery life between 480 and 520 minutes. Whereas Energizer has the same mean, but has a standard deviation of 80, 580, and 420. So if you're asking me, I'm choosing Duracell. Duracell is more reliable in this situation. Duracell is less spread out. Energizer has a much wider, setup here. Yeah, you could get lucky and your battery could last 580, but on the flip side, you could get lucky and your battery doesn't last long and you get a battery that only lasts 420. So I would choose Duracell because of the less spread. Now with our example here, right, without even using, the calculator, if we have a standard deviation, if I add 10,000 to all these numbers, right? So if I look at my range for a moment, 9,500 minus 53,000. So the range here from the highest to the lowest is 37,500. Well, if I add 10,000, 63,000, taking it away from 100,500, I don't change my range. So by adding 10,000 to every number, the spread stays the same. The standard deviation does not change because we're not getting the data to be more distributed, wider, more spread out. So since everything went up by 10,000, the spread doesn't change. But if everything was doubled, meaning that this became 106,000 and this became 181,000, now our spread, our range has gone up to 75,000. Our data is more spread out. The standard deviation doubles in this situation because we're getting more spread, we're getting more varied. So if you change the data and don't change the spread, the standard deviation won't change. But if the data becomes more spread out by doubling or cutting in half or whatnot, that will change our standard deviation.